Looks like we got ourselves a related rate question. So let's get on with the program. It says a cylinder, a cylinder barrel with a diameter of 2 feet contains collected rainwater as shown in the figure above. The water drains out through the valve, a valve not shown at the bottom of the barrel. The rate of change, there's a calculus word right there. The rate of change of the height, I got to do some stuff with that, of the water in the barrel with respect to time t is modeled by this. There's dHdt. Okay, so maybe I didn't need to write that because it's written right there. But it's very important that you always recognize when there is a rate because, it's calculus. We're studying rates. All right, where h is measured in feet and t is measured in seconds. All right, so we got some units there. The volume of the cylinder. Okay, cool. They give us the volume of the cylinder. Now, letter A. It says, find the rate of change of the volume of the water in the barrel with respect to time. Wait, rate of change of the volume. That is dV dt of the water in the barrel with respect to time when the height of the water is 4 feet. Indicate units of measure. All right, so we're going to start with, not this dude, with this dude right here. Because we're trying to find dV dt, so let's write that guy down. And after you write it down, my question is always, all right, are all of these variables changing in our scenario? We know that the volume is changing. We know, the rate or the radius. The radius is staying the same, right? Because we got the cylinder, the radius is not changing. Okay, so that one's constant, and the height is changing. So because R is constant, we can actually plug in what R is. R is 1. The diameter is 2, so that means the radius is 1, which means, 1 squared doesn't do anything, so we just get rid of him, write our h. So let's take the derivative of this with respect to t. Once I do that, I get dV dt on the left side, and on the right side, I get pi times dH dt. Now, let's see. We just took the derivative. Okay, we found dV dt. It says, find dV dt in the barrel with respect to time when the height of the water is 4 feet. So we know that dHdt is this. Oh, yeah, look at this. We know what dHdt, so we could sub this in, and then we could plug in the height for the h. Okay, so that's subbing in the dHdt. Now we're going to plug in the height, which is 4. So now we got dV dt equals pi times negative 1 over 10 times rad 4. Rad 4 is 2. A really quick, easy simplification right there. And our answer is dV dt equals negative 1/5 times pi. Oh, I almost forgot. Units. All right. Whenever I finish a problem, I don't know if you guys have this habit. I double check the end of the question and just to see if I got what it asked for. And it reminds us, hey, units of measure. So we got feet cubed per second. I know it's feet because the height is measured in feet, so these are going to be the units that we're using. And since we're talking about volume would be cubic units. And we have to have per second because this is a rate. So it's volume per time. All right, so now let's move on to B. So for B, it says, when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? Explain your reasoning. So if I want to find if the rate of change of the height is changing, I'm going to need the second derivative of dH dt. Well, actually, the first derivative of dH dt is the second derivative of h. So dH dt, that's the, because I saw a rate of change, and we're talking about the rate of change of the height, so I wrote that out. So I'm going to write out dH dt right here, which is given to us, and I'm going to take the derivative of it with respect to t, to time. So when I do the first, the left side, I get d2h over dt squared. On the right side, I multiply the negative 1 over 10 by 1/2 to get this, and I subtract 1 from the 1/2 to get negative 1/2. But then, remember, we're taking the derivative with respect to t, not with respect to h. So that means we're going to have to use a chain rule and multiply this by dH dt. And since we know what dH dt is, we're going to need to plug that in. So now I have negative 1 over 20 square root of h. That's because this is a negative 1/2, and so I just dropped the 1/2, or the h down, multiplying times with 20, and a 1/2 power is a square root, so there you go. And we know that dH dt is this, given to us by what's inside the problem. So a little bit more simplification. this is what I get. I get 100 or 1 over 200. I don't have any other variables acting on that. So that means that a second derivative is always positive. It is greater than 0 because, so therefore we can say dH over dt is increasing. The second derivative is positive, which means the first derivative is always has a slope of that is positive, that is greater than 0. All right, now let's look at C. Okay, so last one. It says that at time t equals 0 seconds, the height of the water is 5 feet. Okay, use separation of variables to find an expression for h in terms of t. So I saw this separation of variables that takes me back to differential equations. So what we're going to do is we're going to write this dude out. We're going to separate the h's and the t's, and then we're going to do antiderivatives. We're going to use the initial point that they give us to find the h. So we're trying to find a solution to this differential equation. Actually, a particular solution. So here's our initial condition. Let's write out this. I'm already going to put the dt on the side. So it's kind of like multiplying both sides times dt. And then I'm going to get this h to the other side. So we're going to multiply the left side times 1 over the square root of h. And then I'm going to rewrite that to say h to the negative 1/2 power. Then I'm going to integrate that. So I'm going to add 1 to the negative 1/2. So I add 1 to that, I get 1/2. Then dividing by 1/2 would be multiplying by 2. And don't forget your constant. On the other side, I do the same thing. I do the antiderivative of negative 1 over 10. I get t, and there's my constant right there. Let's combine the constants. So this is c sub 3. And then let's get h a little bit more alone right here. I'm going to multiply both sides by 1/2 so that I don't have, actually, that shouldn't be c3 anymore. That should be c4, c sub 4. Because it's like I'm multiplying this by 1/2, so that constant changes. C4 is different than C3. All right, so now let's plug in our initial condition. When I plug in our initial condition, I plug the 5 into the h, and then I plug 0 into the t, and I find out what C sub 4 is. Okay, now I know what C sub 4 is. I just need to go back to this line right here, plug in the square root of 5, because that's what 5 to the 1/2 power is, and then finish getting h alone. So let's get some room over here and write that out. Plug in the C sub 4, and then I'm going to square root both sides to get rid of the 1/2 power. And so now I have h of t equals that. So actually, not writing C sub 4 wouldn't have hurt me, but it is more proper. And that's your final answer. And then we got the scoring guide just in case you want it.